Hi, you guys. We're going to start out in respiratory by looking at gas exchange and transport. That's really important as to how it is that oxygen gets to where it needs to get in the body, more so than the anatomy of the system, which you can get in an external video. So what we're going to be looking at is the property of gases, gas exchange, how it goes from place to place, how you transport oxygen, how you transport CO2, because you do it actually in quite a different way. So the first big thing that we want to remember is that the movement of gas, right, oxygen, carbon dioxide, anything, it differs whether it's in air or in liquid. And that makes sense, right? If you're trying to move an air bubble in the air or you're trying to move this air bubble underwater, it's going to be quite different. So that's what we have to do. We have to bring oxygen in from the air, and then we have to get it into a liquid, which is blood, which is mostly water, and transport it in water. That poses a difficulty, okay? So what influences the efficiency of this movement is what we want to look at, and we're moving oxygen through air, more specifically alveoli, and then through fluid into the blood and then from the blood into the tissues. It's kind of like barrier after barrier after barrier that we have to accomplish. So for this to be efficient, it's going to depend on the structure of the respiratory membrane, right? How healthy that all is. The surface area of the alveoli. So these are the alveoli, these little balls at the very end of your respiratory network. That's where gas exchange is going to be happening, where we're going to be absorbing oxygen, getting rid of CO2. So how is that surface area? Is it healthy and viable and usable, or does this individual have fibrosis? Has been smoking for 50 years, has fibrosis, and this is sort of closed over and passage isn't really happening. So surface area, very important. This is not moving. Look at this, concentration gradient or partial pressure. What's a concentration gradient? It's how much of that oxygen is present for you to be able to use it. How much are you actually breathing in? Are you successful at doing that? Are you getting it in? Are you at high altitude where the pressure is low? All that is going to matter. So here is that high, pressure of CO2 in the alveoli. Let's say you've been very efficient. You've brought it into the alveoli. Now you're going to transport it. Is that, pressure adequate there? If, for example, you had, and I've colored this in here, this is a person who worked with asbestos, let's say, all their lives, and they have this thickening here of the alveoli from this assault, which has happened from this asbestos or coal or any kind of sort of aggressor like that. That surface area is going to be reduced. The transport of oxygen is going to be reduced. So that membrane can be thick. So number 3, I'm calling membrane thickness. Okay, how efficient that is, because the thickness is going to not allow that oxygen to come through. And a distance that it has to travel. So if we have the same diagram again, and all of a sudden there's fluid. I made it in yellow, I colored it in. Let's say there's a lot of fluid in there, you're congested, there's fluid all over your lungs, and now that oxygen needs to travel into the blood bit through a greater distance because it's been floating there in this extra fluid. That's going to make it more difficult. So backtracking, how do we measure gas concentration? How do we know that we have this concentration gradient? Well, it's the same thing that we've been talking about, concentration gradient, but this time we're going to call it partial pressure because it's a gas, right? Pressure, partial pressure. Why partial? Well, because we have lots of gases in this air that we're inhaling. So we're more interested in what is the pressure of oxygen, right? So as a definition in partial pressure, it expresses gas concentration in a solution and allows a comparison with partial pressure in the air and in the fluid, which is what we're, again, alveoli and blood. Okay, so partial pressure of CO2 in the blood is illustrated here. We have a partial pressure of carbon dioxide also circulating around in your blood, and now you have excess. If you have excess, it's because you've just been metabolizing. It's normal things that you're doing in the body, and you have excess of the CO2 buildup. The partial pressure has increased here, and now you want to deliver it into the alveoli because the pressure of carbon dioxide is greater in this vicinity than in this vicinity, and it's going to cross over. Okay, so those two partial pressures are so important. Again, why is it partial? Because it's exerted by a single gas. We're talking about what is the partial pressure of oxygen? What's the partial pressure of carbon dioxide? Okay, and we're measuring that in millimeters of mercury. The atmospheric pressure, right, that's what you're breathing in, is the combined pressure of all those partial pressures of all that, those atmospheric gases. So we know that the atmospheric pressure at sea level is 760 millimeters of mercury. That's what it is here in Aptos, in Santa Cruz, around here. We're at sea level. So what is it that we're inhaling? Well, mostly nitrogen, 79%, 21% oxygen, and then tiny bit here, less than 1% carbon dioxide, argon, and then all others here. Okay, so just remember that the majority of that is nitrogen. So it's making up 79% of that air that you're inhaling. So what is the partial pressure? Okay, we want to know what the partial pressure is of that particular gas, not as a group, particular. So the partial pressure of nitrogen is 79% of 760 millimeters of mercury, which is what the atmospheric pressure is. So we multiply these. What is 79%? 0.79 times 760, and that's going to give you a partial pressure of 600 millimeters of mercury. Okay, why do we need that? I'll show you later. Okay, for now, just get that idea that these partial pressures are different. Let's do it for oxygen. Oxygen then is 21% of the air that you're inhaling. You're multiplying that by the atmospheric pressure, 760 millimeters of mercury, and you get 160. Okay, so 160 millimeters of mercury is what, in a sea level, the pressure at sea level of that oxygen that you're able to take in. What is it of carbon dioxide? We need to know that one too. Less than 1%, and that turns out to be about 7.6 millimeters of mercury. Hold those ideas now. You have that number in your brain for oxygen, 160. Okay? Right. Now, let's say you're not at sea level. Let's say you're up in the summit. You're up in Everest, where the altitude is 29,000 feet. Okay, that sounds terrible, huh? The atmospheric pressure, not 760. It's 253 millimeters of mercury. So now let's do those calculations, right? What would the pressure be? And the oxygen pressure, when you multiply the 21% times the 253, is going to give you 53 millimeters of mercury. That is very low. Keep that number in your brain for when we look at what kind of pressures are needed for it to actually cross in the alveolus. Just some ideas of other cities to put it into context for you. Mexico City is really high. It's 7,000 feet. Atmospheric pressure is 589. So you can calculate these. Denver, 1 mile high. I want you to calculate those and see what it is. When you do go to Mexico City or Denver and you run up those stairs, oh my gosh, you are out of breath because you don't have enough of that oxygen. So as a giveaway there in Mexico City, it's 123. In Denver, it's 132. So it's you're more out of breath in Mexico City than in Denver. Okay, so we've done that in air. Now, what about partial pressure of gas in a liquid? Well, it depends on how much of the gas is dissolved in the liquid, right? How much pressure of CO2 in a can of soda? Well, it depends on how much was actually dissolved in it, because it does dissolve. If a gas is under pressure, it's placed in contact with water and it move into water. So in order to make your Diet Coke, this picture is there, what's going to happen is that they're going to put it under really high pressure and pump in that CO2 and seal it so that it stays in solution. And then once you open it up, you've taken away that sort of trapped in CO2, you open the can and it starts losing that CO2. So we need to dissolve it if we're going to transport it. So this is just interesting stuff about the can of soda, because it's the same thing. And like champagne is a huge amount of pressure that they do. They just sort of pump in the CO2 and then seal it, because we find it, but we like the bubbly. Okay, so what factors affect the movement of the gas into a liquid? Because that's what we need to do. We need to dissolve it and move it in blood, right? What matters is the solubility of that particular gas, and it's different from oxygen and CO2, quite different. The temperature, well, that's not going to vary that much, right? Because you have body temperature, and it's going to be very stable because of homeostasis. In your can of soda, it's not so. You leave it in the fridge, the carbonation stays longer. You leave it outside, right, warmer, it's going to lose more of it. And the pressure gradient of the gas. So how much pressure, how soluble, and whether you're in the correct temperature. So this cut off a little bit, dissolving oxygen in a liquid. Then if we had oxygen here, 100 millimeters of mercury, let's say, and you put it in contact with water, how much of it is going to dissolve? Well, a certain amount of it dissolves, but notice that the pressure here is going to be different, so that we don't have equal number of molecules when it is in a state of equilibrium. No more is going to dissolve. In this case, no more is going to dissolve. That's equilibrium, but the number of molecules is not the same. Okay, that's important to know. Carbon dioxide is 20 times more soluble in water than oxygen is. Much more easy to transport CO2 just dissolved in the blood as we do. Oxygen is not very soluble, so we need something that's going to help transport it, because it just will not dissolve in that water, in that fluid, in that blood. Okay, so you need a different molecule to help you do that. And that different molecule is hemoglobin. I'm going to stop this right now, and then we'll continue on with these ideas in a subsequent video. Thank you, guys.